So today's SI class is the first SI class of PHYS Field 51. And today's SI class has two questions. One is about a one-dimension heat diffusion. Another one is about Sturm-Liouville boundary value problem. The SI class material you can find on the blackboard. So let's begin. In question one, there's a 1D heat diffusion. First, there is a watt in here. This watt has a length capital L here. On the left-hand side, it's maintained at zero temperature. So this part, the T is 0. And on the right-hand side, it's thermally insulated. So in the other end, the Ts here is 0. And the initial temperature is a function Fs here. So in this question, we're gonna use the heat diffusion equation. In 1D, we're gonna use this equation here. And the boundary condition on the left hand is with s equal to 0, is the temperature is 0, and at s equal to L, it did not have any heat flow. So look at this boundary condition. This boundary condition is a base condition, so it's a kind of Sturm-Liouville problem. And the initial condition is this. At time equal to 0, the temperature is equal to Fs. You can see that because we are using the heat diffusion equation, the coefficient in the problem is relatively simple. We do not need to use the complicated form in the lecture notes, which about the Sturm-Liouville problem. So we can just separate it normally. First, we describe the temperature using the multiple of the position part and the time part here. And then we substitute to the PDE, and then we will get this. Oh, forget to mention the kappa here is the thermal diffusivity. And this 2 is equal to the lambda here. First, we solve the time part first. This theta is equal to the theta log times E times the potential term of with a power of lambda times kappa times T. In here, because the kappa and T are both larger than 0, so if lambda also larger than 0, this term will blow up into infinity when time becomes infinity, which is not physical. So the lambda has to become smaller than 0. And here we let the lambda equal to negative mu square. So the theta term become beta log times. And then we solve the position part. The x prime prime equal to negative mu square times x. So the general solution for this is combination of sine function and cosine function. Okay. After solving the general form of the answer, then we start to fit the boundary condition into the equation, into the solution. Here, the boundary condition we have is these two boundary conditions. So x as 0 has need to become 0. Because the sine part is equal to 0, only the cosine part is left. So b is also equal to 0. And then we solve the derivative part. The x prime as x equal to L is equal to 0. We differentiate the child solution first. This x prime is equal to mu times a times cosine function here. For the cosine function equal to 0, then mu L need to become equal to this. And n is equal to any positive integer. So the mu is equal to this. Then we combine the position part and the time part. So the solution now becomes this. So now we need to get the coefficient an here. To define this an, we need to use the initial condition. The initial condition in this problem is at time equal to 0, the temperature at S is equal to function x here, which is also equal to this. The exponential part become 1 here. So in this part, we multiply both sides by this side function here. So it become a form like this. And then we integrate both sides from 0 to L. On the right hand side, because of a cardinality of the eigenfunction. Oh, I made a mistake here. This is not square here. This should be one side here, and the side is outside the summation. Oh. Space. And because in the right hand side, because of a cardinality of the eigenfunction, only an, that is when this part and this part have the same n, the term is equal to 1. If not, they are equal to 0 because of the orthogonality. Oh, maybe I should use other notation here. M equal to n, and this is the m. I changed the summation to m here. Here. And then you get this. Just an here. I don't use any. So overall, the solution will become a summation of function. So the final solution is this here. Do you have any question about question 1? If yes, you can type it in the chat or unmute yourself and then ask. Oh, I think the middle part I should be more specific, be more detailed. So this a little more detail about what's the integral is going on. So no one has problem about question 1? Okay, then let's move on to question 2 here. In question 2, we considering Stern level boundary value problem as defined in the lecture notes. And we suppose there is a lambda is a degenerate eigenvalue that has 2 eigenfunctions, y1 and y2 here. So let me write down the boundary value problem as defined in the lecture notes. And the boundary is like this. And the initial condition is also a function x here. Because in question 2 we consider in only position part here. So I directly use the position part of the ordinary differential equation after this using the separation of variable. So u is equal to dt times y is here. And the position part of the ordinary differential equation is not like this here. And in this question, we suppose there is a lambda lot here that it has two eigenfunctions for it to that is satisfying this equation here. This. And what we want to do is to prove PHYS with a bracket times y1 times y2 minus y1 prime times y2 is equal to some constant. So the equation, the ordinary equation actually can be simplified into a linear homogeneous differential operator L here. This L is equal to this plus QS times Y. Also equal to lambda times RS times Y here. Because y1 and y2 are both solutions of this equation, so their equation, their equality of them here, equality, and then let's move on to the next page first. So first we write down this term here. The lambdas times y1 times y2 minus itself. So obviously this part is equal to 0. And then we do a little trick here. In the first term, we let lambda y1 equal to the differential operator of y1 here. And the second one, we do the same thing, but to the y2. And then we expand the differential operator. And then you will get this term. The second term and the third term cancel out each other. And then we add two terms in the middle, which equal to 0 here. The first term we add is y2 prime times px times y1 prime. To maintain the equality, we need to add a second term. In the first two terms, we can bring that together to become a derivative of px times y1 prime times y2 prime, right? Times y2. Yeah. And we do the same thing for the third term and fourth term. So overall, this term becomes this. And this term is equal to 0. So if we integrate it, we're gonna get a constant term on the right hand side. So that's how we prove this term is equal to a constant. So this the end of part A. Do you have any problem about it? Okay. Then we move on to the part B of the question 2 here. This time we need to show y1 is equal to ky2 here. And k is some non-zero constant. In this part, we need to use the boundary condition. And we only use the boundary condition at x equal to 0 only here. By using these two boundary conditions, we can relate the y1 prime and y1 at x equal to 0, and same for y2. Then we And we need to use back the result in part A, which is PHYS times y1 times y2 prime minus y1 prime times y2 is equal to some constant. And this identity is applying for s between 0 and 1 here. So at the boundary, it also apply. So we substitute the equation 1 and equation 2 into it. And you get this result. Obviously, on the left-hand side is equal to 0. So the constant is equal to 0. Because we calculate the c is equal to 0, that means for all x along from 0 to 1 here, is the whole identity still hold here. Because this identity hold for all pairs, so what's inside the brackets is also equal to 0. And then you get this identity. That is y1 prime divided by y1 is equal to y2 prime divided by y2 here. So in here, we can conclude that the y1 is equal to k times y2. So this is the end of the part B here. Do you have any problem? Okay, seems no one has a problem about question 2B. So if you have anything about any problem about electrolux or other things, you can also ask how to get C equal to 0. Okay, someone asked how to get C equal to 0. So in the middle part of this page, we this identity originally is for all x from 0 to 1 here. And then we focusing on s equal to 0 here. And then we substitute the equation 1 and equation 2 into this identity. So that's how this equation you get. Because on the first term, there's a negative sign and the second term is a positive sign, but actually they are the same. So they cancel out each other. So you get C equal to 0. And because this C is same for all x from 0 to 1, so for other x on between 0 to 1, they are the constant is also 0 here. So did I answer your question? So let me answer the second question first. Does this mean that eigenvalue has one eigenfunction only? Yes. Yes. This is about the uniqueness of the eigenfunction. Any more questions? If not, you can, this is the end of the side class, and you can leave now.